Please, can you hear me now? Please let me know in the comment section if you can hear me. Please, can you hear me? Okay, okay. Someone is. Please, can you hear me now? Is it audible? Can I see yeses in the comment section if it's audible? Okay, I think I can carry on. All right. Thank you very much. Okay, so good evening, guys. Good evening once again. In today's section, we are going to consider nothing. So I've had a lot of people coming to me um to tell me they are not getting the Norton theorem very well. And so I think it's important we take a step back to revise this one before we go back to the AC we were doing the last time. All right, so let's carry on. So Norton's theorem, it states that any linear circuit connected between two terminals can be replaced by what we call the Norton's current connected in parallel with the Norton's resistance. Okay, let's continue. I'm going to explain this further. All right, good. So Norton's current is the IN. Okay, it is a short circuit current and it's connected between the two terminals. Now, which terminals am I talking about? So, anytime you are given a question to solve using Norton, most of the times there is a particular resistor, the load resistor, and that is the resistor you are mostly asked to find the currents passing through. Okay, so we are going to consider it and then talk about it briefly. But then these are the most important things you should take notice of anytime you are given a question to solve using Norton. It's the Norton's current as we have here, the Norton's resistance. Okay, so this is also the total resistance or the equivalent resistance as seen from the two terminals. Okay, so looking at this circuit down here, you can see there is an open terminal between A and then B. Okay, so the load resistor was connected here. Now, as I said earlier, there are three things you need to take notice of. We have the Norton's current, the Norton's resistance, and then the current passing through that load resistance. So we are going to consider it briefly. All right. So to solve any question using Norton, there are some steps you would need to follow. Okay. It is very important to take notice of these steps so that you don't get it wrong. So we are going to solve a number of questions, about five or six. But then before that, I would want us to go through this first so that at least we get to know the steps before we carry on. Okay. So to solve any question using Norton, the first thing you're supposed to do is to remove the resistor from the circuit and then mark the two terminals. Now, what resistor am I talking about? I'm referring to the load resistor. Okay, so they are always going to tell you find the current passing through this particular resistor. Okay, so that resistor becomes your load resistor. Okay, so the first step is asking us to remove the resistor from the circuit. Now, in this question, the load resistor was 3, the 3 ohm resistor you are seeing here. So see something. They took it from there. Okay. They took the resistor from there. That is the very first step. You remove the resistor from the circuit. All right. Let's continue. Now the next step is asking you to mark the two terminals A, B. So once again, we've taken the resistor from there and then we've marked the terminals A and then B. Let's move on to the next step. Now, the next step is asking us to find the short circuit current through the two terminals by applying KVL. Now, it is very much advisable to use KVL. It doesn't mean it's always the case. Okay, so you are going to see, moving on, there are some questions. I think we have an example in there. We are going to consider it shortly. There are some examples that it's not like when you use KVL, you're not going to get the answer, but it's much advisable to use some other techniques. Okay, that is why we considered those techniques before coming down to these theorems. Okay, so the next step is asking us to find the short circuit current passing through the terminals. So you take away the resistor, that is your load resistor, and then you put your IN there. Okay, you put your IN there through those two terminals. Okay, let's move on. Now the next step is asking us to, okay, so yes, and after you're done, you apply KVL to find IN. So that is this for IN. Let's move on. So like I said, there are three main important things you are required to find anytime you are given a Norton's theorem question. It is the IN, the Rn, that is the Norton's resistance, and that is what you are going to consider right now. Okay, so in calculating the Rn is the same as the total resistance. Okay, total resistance when all sources have been deactivated. Now, this is very important. Okay, before you find your Rn, always make sure your sources are deactivated. All right. Now, if it's a voltage source, what we do is we short circuit it. Okay. And if it is a current source, what we do is we open circuit it. So we are going to consider a number of questions very soon. Questions that do involve current source and then voltage sources, so that we get to know how to go about it anytime we come across a question like that. Okay, so let's find Rn. Of course, because these are voltage sources, we are going to short circuit them, this and then the 35V here. And after we are done, we are going to stand here, looking through here, and then find Rn. Alright, so standing at the terminal, you are going to find Rn. And Rn, as I said earlier, is the total resistance. After you are done, you are going to reproduce the Norton's equivalent circuit. Now, it is very much important you know how to draw this equivalent circuit, because before you can find the current that's passing through the load resistor, you would need to reproduce this Norton's equivalent circuit, and then using current division, you find the current that is passing through your load resistor. So the load resistor was 3 ohms. Okay, that was what we took from there. So after we are done, we are just going to draw this simple and nice circuit where we have the Norton's currents connected in parallel with the Norton's resistance and the load resistance. Now don't forget, this one here is the one we take from the circuit. So in this case, it was 3 ohms. So after we are done, we bring it back, and then this is our Norton's current. Using current division, we can find the currents passing through this branch. Now let's say the currents passing through that branch is the I here. If you want to find the current passing through this 3 ohm here, current division. I hope you all still remember current division. Yes, those techniques are very important. They are the techniques you are going to be using to solve questions in these theorems. So if you've forgotten about them, I think you would need to revise. Okay, if you've forgotten about them, I think you would need to revise them because most of the times in these questions, we just make the analysis and then refer to the techniques we've learned earlier to solve it. All right, so let's carry on. So these are the basic steps you'd need to be able to solve questions in Norton. So I'm just going to display the questions you have for tonight and then start solving them quickly. All right, so moving on to our very first question on Norton. So this question is asking us to find the currents that is passing through the 7 ohm resistor using Norton's theorem. Using Norton's theorem. Okay, let's find the current passing through the 7 ohm resistor. So in this case, 7 ohm resistor is the resistor you are supposed to find the current passing through. Okay, so that becomes our load resistor. Okay, that becomes our load resistor. So Norton is asking us to first take away that resistor and then put IN. That is the Norton's short circuit inside there, and then we work for our IN. After we are done, we are going to open circuit that part, put our RN there, deactivate all sources, and then find Rn. Okay, and after we are done with that, we put everything inside the Norton's equivalent circuit and then solve for the current passing through it. Alright, so very quickly, let's solve this question we have right here. So solution. Step 1. You are supposed to remove the load resistor and put IN there. So let's draw the circuit again. This is how it's going to look like. I hope you all get it. So this time around, I'm not going to draw my resistor, the 7 ohm resistor there. I'm going to replace it with IN. Okay, that is the very first step. And then we solve for IN. So with this, you ask yourself, which technique can I use to solve for IN? As I said earlier, it's not always that you need to use KVL. For example, looking at this question carefully, you realize that IN is the current passing through this 2 ohm resistor here. Okay, it's the same current here. Now we know the total current coming to be 12 amps. If we should use current division, it's going to be way simpler, right? Good. So to find the current IN, that's the current passing through this 2 ohm resistor here. You can say that IN here is equal to, now we consider the other resistor inside that P connection, that parallel connection. So 4 over 4 plus 2 times the total current, which is being divided, 12. Okay, so what do we have for IN? 8 amperes. I hope you all get it. That is it for IN. So let's find RN. And please, if you don't get anything, you can just prompt me in the comment section so that I go over. Let's consider Rn. Now, Rn is a total resistance, okay? When all sources, so you can't find your Rn keeping the sources inside. For example, voltage sources do have internal resistance, which may, practically um, affect your total resistance. So it is very important you don't forget this rule. When all sources have been deactivated, okay, deactivated. So if it's a voltage source, you short circuit it. If it's a current source, you open circuit it. So let's find Rn. So we can see that there is a current source here. Okay, so what you are going to do is you are going to open circuit it, right? So let's redraw it. This is 4 ohms. Now we are going to put Rn where we had the load resistor. Okay. Now I'm going to open circuit this part because it's a current source. Okay. So now how do we find Rn? Rn is the total resistance. So this part has been open circuited. So obviously current is not going to come this direction. So we are going to have 4 and then 2 to be connected in series. Okay, since it's the same current that will flow through this. So standing at Rn, looking through this um open part here, the Rn is 4 plus 2, which is equal to 6 ohms. Okay, so we have In to be 8 amps and then Rn to be what? 6 ohms. Now the question is asking us to find the currents passing through this 7 ohm resistor here. Okay, how do we do it? We do that by drawing the equivalent circuit. Okay, so I'm going to draw the equivalent circuit. This is how it looks like. Now this is my In. Now what was In? In was 8. Okay, In is connected to Rn. What's Rn? We had 6. It's connected in parallel with now the load resistor, that is the 7 ohm resistor, the one we took from there. 7. Okay, this is how the equivalent circuit is going to look like. Now, how do we find I, the current passing through the 7 ohm resistor here? Once again, we can use current division. Now, the total current coming is 8 amperes. If you want to find I here is equal to, now the opposite one, 6 over 6 plus 7 times the total current, which is our Norton's current, 8. And what are we going to get? 3.692 amps. Please, if you don't get anything, you can let me know in the comment section so I go over. Okay, so yes, let me go over it a bit. So the question is asking us to find the currents that is moving through the 7 ohm resistor inside here using Norton's theorem. Okay, so before you can find the currents that is moving through the 7 ohm resistor here, you need to produce the Norton's equivalent circuit. Okay, and to be able to produce the Norton's equivalent circuit, you need your IN, that is the Norton's current. You need Rn, that is the Norton's resistance. And then after you're done, you can draw the Norton's equivalent circuit, fixing your values, and then you can find I using current division. Okay, so the processes I'm going to go over again are the processes we use to find the IN, the Norton's current, and Rn, the Norton's resistance. So I said that before you can find IN, you first need to ask yourself which of the resistors is the one in question, which of them is the load resistor. Okay, now the question is asking to find the current passing through the 7 ohm resistor. So that becomes your load resistor. Do you get it? So in calculating your Norton's current, what we do is we put a short circuit where the load resistor was, and that is the short circuit we have here. Okay, so you're going to put the short circuit here and then write IN there, and that is the IN we are going to find. Okay, now looking at the circuit, IN is the same as the current here because it's coming from here, passing down here, and then I hope you get it. Yes. So how do we find IN? Now looking at this, we can use current division. Okay. Since IN is a current passing through this branch, now current division, we consider the other resistor. So in this case, since you have 2 and 4 connected in parallel, and then we are trying to share the current, we consider 4. Okay, so 4 over 4 plus 2 times the total current which is being shared. In this case, 12 amperes. Hope you get it. So that is how we got our IN. So 4 over 6 times 12, which gave us 8 amperes. Do you get it? Good. Now, finding your Rn. The Rn is the same as the total resistance when all sources have been deactivated. Okay, so now we go back to our question and then we deactivate all sources. Okay, now I said that if the source in question is a current source, we open circuit it. Now, open circuit literally opening it. Okay, so that is what we have here at this part. Sorry. And if the source is a voltage source, we simply short circuit it. Okay, good. So you are going to open circuit here, and then you are going to put this time around, you're going to put Rn here where the load resistor was, and that is the circuit I've drawn here. Okay, now how do we find Rn, the total resistance? Now, since this part has been open circuited, current is not going to come this direction at all. Okay, so essentially you are going to have the circuits looking like this. Okay, let me clean that portion so you see it clearly. So essentially, this is how the circuit is going to look like. Okay, this is what you are going to get. And then we find the total resistance looking at it this way. Okay, now considering this circuit you have here, this circuit, say A, them by short circuiting them. Okay, so let's do that. So I'm going to draw my circuit again. This is how it's going to look like. So I'm going to have my Rn here. Now, how do we find the Norton's resistance? That is Rn. Now looking through here, we can see that Rn, which is the total resistance, is equal to 10 here connected in parallel with the 10 here plus 15, since it's going to be in series with this 15 here. This 10 here is going to be in parallel with this 10 here, but it's going to be in series with the 15 here. Now what are you going to get? Product over sum 10 times 10 for resistors connected in parallel plus 15, and I'm going to get 20 ohms. So that is the Rn. Now let's find In. Now in finding In, I'm going to put my In here. Okay, I'm going to put my In at the terminals where the load resistor is supposed to be. In this case, they didn't put any load resistor there, but then they've given us that open terminals to be used. Okay, so I'm going to put my In there, and then I'm going to solve for In. Okay, so let's draw the circuit again. This is how it's going to look like. Now in finding In, we don't short circuit anything, so I'm going to bring back my 100V voltage source. It's in finding the Rn that we short circuit them, because as I said earlier, some voltage sources do have internal resistance. So if you don't short circuit them, practically it's going to affect the total resistance you are going to get. Okay, so this is my In. Good. So after you are done drawing the circuits, you ask yourself, which technique, sorry, here is 100V, let me write it. Which technique can I use to find my In? Now, I can choose to use, once again, current division because I think it's simpler. Okay, In is the same current passing through this branch here. So let's use current division. Now, using current, sorry, using current division, In is equal to, since we have 10 connected with 15 in parallel, and then I'm trying to find In, the current passing through 15, I'm going to consider the other resistance. So I have 10 over 10 plus 15 times the total current. Now, do I know the total current? I don't know the total current coming, but I know my total, I know the total voltage source inside. Okay, so let's revisit Ohms. Using Ohm's law, V is equal to IR. I can find my total R. Okay, RT. For RT, I have this 10 here connected in parallel with 15 here. So 10 parallel 15 is going to be in series with the 10 up here. So plus 10. And I'm going to get 10 times 15 over 10 plus 15 plus 10. That's what I'm going to get. Please, what are you going to? Can somebody punch it and then tell me? Is it 16 ohms? Alright, so if that is RT and V is equal to IR, then we can find the total current, which is V over R. Okay, so we have 100 over R, which is 16, right? Okay, so we are going to get the total current to be what? 6.25 amperes. Okay, so now let's bring it here. IN is equal to 10 over 25 times 6.25. So what's IN? 2.5 amperes. Okay, so right now we found Rn to be 20 ohms and then In to be 2.5 amperes. The question is asking us to develop the equivalent circuit. So we are just going to once again draw the Norton's equivalent circuit, and then we are going to fix our In value there, and then our Rn, and then we connect it to the open terminals. Please, any question up to this point? Okay, so since we found In and then Rn, In was 2.5 and then Rn 20 ohms. We can now develop our Norton's equivalent circuit, right? So Norton's equivalent circuit. Now, this is how it's going to look like. The Norton's current, which was what? 2.5 amperes, connected to the Norton's resistance, that was 20, in parallel with. So in this case, the RL was the open terminal there. Okay, so A, B. Okay, so that's it for this question. Please, if you have any question, you can let me know. If not, then we tackle our last two questions. Please, any question. If I can continue, you can let me know. Just say continue in the comment section. Okay, so I'm going to go through the last question with you. So I'm going to take my time and then hopefully this one explains it very well. And also I'm going to send the solutions to you right after I'm done with this section. So yes, I'm going to go through this question and I'm going to take my time and go through it as slowly as possible. So this question here is asking us to use Norton's theorem to find the current that is passing through RL. Now this is RL, the 4 ohm resistor here. We are supposed to use Norton's theorem to find the current that is passing through it. Okay, so let me make the division here. So solution. Before we can find the current that is passing through this branch over here, we need to draw Norton's equivalent circuit and then find that current using current division. So now this is a question, this is a circuit I'm talking about. Before we can find the current I passing through this 4 ohm resistor, we need to be able to draw the circuit, develop the circuit. Okay, before we can find that current. Now inside this circuit, we have IN. That means we would need to find IN. We have Rn. That means we would need to solve for Rn. And then RL, which is the load resistor, is 4 ohms. Okay, because that is the resistor we are trying to find the current through. Okay, so our task here is to find IN, find Rn, and then come and put it in this circuit, and then find I using current division. Okay, all right. So let's move on. We are going to find Rn first. Okay, now Norton is saying that to find your Rn, that is the total resistance, you deactivate all sources. Okay, so if there is a voltage source, you short circuit that voltage source, and if there is a current source, you open circuit the current source. So given this question, in finding Rn, I'm going to short circuit the 26V here, and then over here I'm going to open circuit this 6 arm here. Okay, so this is how my circuit is going to look like. Sorry, the load resistor is not going to come. Okay, so you are going to deactivate all sources, and then inside where your load resistor was, you are going to put your Rn there. Okay, so that is where you are going to stand and then find the total resistance. And then everything else remains intact. But then because there's a current source here, I'm going to open circuit the current source. Okay, so this is how it's going to look like. I short circuited this 26V from there. That is why this part is like this. Now there is a current source here, and for current sources we don't short circuit them, we open circuit them. Okay, so I did that here. That is why I have this here. So this is 6 ohms, and this is 3 ohms. Okay, this is also 3 ohms, and then 5 ohms. Now how do you find Rn? Once again, Rn is the total resistance. Okay. Now, because there is an open circuit here, currents won't come to this part. Okay. So the 5 ohm here and the 3 ohms here, they are all going to, in essence, not be of any use, since there is not going to be any currents coming in them. Okay. Because there is an open circuit here, currents won't come this direction. Okay, so Rn is going to be the 6 here connected in series with the 3 here. So we are going to have 6 plus 3, which is 9 ohms. Okay, now the next thing to do is to find In. Alright, now to be able to find your In, Norton is saying we should take away the load resistor and then put the In there and then solve for it using KVL or any other technique that would be able to help us find our In. So the next thing to do is I'm going to redraw my circuit and then put the In, that's the Norton short circuit current, where my load resistor was. Okay, so I'm going to draw it again. And I'm going to bring back my voltage source. And then because this is where my load resistor was, I'm going to replace it with this. Sorry for the curved line. Okay, good. So after you are done with this, the next thing to do is to find In. So you can choose to use, I think you can be, yeah, I think you can use KVL to solve for In, and then you can use superposition as well. Yes, yeah, you should be able to use superposition. Um, okay, let's try that. So now the goal here is to find In. Okay, so the technique that's going to help you find In, you choose it. Okay, so yeah, I think we can use superposition when the 26 V is acting alone, and then also when the 6 amperes is acting alone. So yes, let's use superposition. So using superposition. Now superposition theorem states that anytime you have multiple sources inside a circuit, okay, you can make each one of them act alone and find the currents passing through that branch separately. After you're done, you add them. Okay, so in this case, I can make, let's make the 26V act alone first. So this is how it's going to look like. The 26 voltage source is acting alone. Now when it's acting alone, what you are going to do is you are going to deactivate the other source, since we want just the 26 to act alone. Now since it is a current source, I'm going to open circuit it. Now I'm going to call this In prime, okay, because that is the Norton's current when just the 26V is acting alone. So I can solve for In prime. After I'm done, I'm going to make the current source also act alone, and then find once again In prime prime, and then after I'm done, I'm going to add them together. Okay, so this is also 3 ohms. Now let's find In prime. We can use um basic Ohm's law, okay? V is equal to IR. Now, when current is coming and then it gets to this node, ideally it's supposed to split. But because it's seeing an open circuit at this point, it's not going to come this direction. So everything will come through this short circuit here and then back to the source, okay? And also, the fact that there is a short circuit there also mean when they get there, it's going to go through the short circuit, okay? So V is equal to IR. So 26, which is my voltage source, is equal to the I. Now, the I here is the In prime because it's the same current passing through the 6 and then back. So you have In prime times the resistor. Now, the resistance, total resistance, we have 6 and 3 connected in series. So 6 plus 3 connected in series. Okay, so 26 is equal to 9 In prime. Okay, so I'm going to divide here by 9, here too by 9. What am I going to get for In prime? 2.889 amperes. Okay, now this is the Norton's current when 26V is acting alone. Now the next thing to do is to find it when now the 6 amperes current source is also acting alone. And after I'm done, I'm going to add the 2. Okay, so let's do that down here. Now, since we want the 6 amperes to act alone, we are going to short circuit the 26V voltage source. Now, when we're doing for 26, we open circuited the 6 because it is a current source. But for voltage sources, we short circuit them. Okay, so let's do that. So I'm going to draw the circuit again. This is how it's going to look like. Short circuit. Now this In here is In prime prime. That is when the 6 amperes current source is acting alone. Okay, good. Now looking at this circuit, since there is a short circuit here, when the current is coming and then it gets here, everything will pass through here. So the 6 amperes, that is the source that is being produced, is the exact same 6 amperes that will pass through the In prime prime here. So essentially, your In prime prime is also 6 amperes. Okay, so the total In, that's the Norton's current, is equal to In prime plus In prime prime. What are we going to get? 6 plus 2.889, which is equal to 8.889 amperes. Let me write it here. In is equal to 8.889 amperes. Alright, so right now we found Rn. We had Rn to be 9 and then our In to be 8.889. So we can find the current. Okay, so let's go back to this circuit. Let's come back to this circuit. Now we have In here to be, we had In to be what? What's the value of In? 8.889. What was the value for Rn? 9 ohms. Now RL is 4 ohms. Okay. The question is asking us to find The question is asking us to find the currents passing through. Now the question is asking us to find I, this I here, the currents passing through the load resistor. Okay, now we know IN, so we can use current division to find that current. Okay, so I is equal to, now in current division, anytime we have two resistors connected in parallel, we consider the other resistor. So in this case, we have 9 over 9 plus 4, that's the load resistor, times the total current being shared, 8.889. Now what's going to be the current? 6.153 amperes. So this is the current that is passing through the load resistor here. Please, is it okay? Any question?